Hello and welcome to this tutorial about the SICK 3D belt pick sensor app running on the Trispector P1000 3D camera. In this tutorial we will show you how to configure this sensor app so that a robot can pick products from a conveyor belt in a safe and reliable way. The 3D technology allows for a reliable detection and gentle handling of the products. As the true shape of each product is detected, safe and more accurate picking of the product is possible, leading to a higher product quality. In this tutorial we work with a trial version of the sensor app, but the configuration is exactly the same in the full version. The first step is to install the camera over the belt. We have the Trispector P1000 with an attached encoder cable, an Ethernet cable and a power I/O cable. We also have an encoder and an encoder splitter, so that both the picking system and the camera get the same encoder input. When mounting the camera, we need to consider the camera height and the object height. The camera needs to be placed so that the product fit in the camera's field of view, across the width of the belt. Here we have mounted a Trispector P1060 camera about 700 mm above the belt. This gives us the possibility to cover approximately 600 mm of belt width. To establish a connection, the camera and the computer need to be on the same subnet. For further instructions, please have a look at the SICK Ethernet adapter configuration video. We use the SICK App Manager to install the sensor app on the camera. With the SICK ID, the App Manager can be downloaded for free from sick.com. To get a SICK ID, select Register. When logged in, locate the 3D belt pick sensor app in the app pool. Select the device and install the sensor app. Click on Scan if the device is not already found. Then click on Download and Install. Now we can open the 3D belt pick sensor app in the Chrome web browser. Type in the IP address of the device. The configuration interface contains 6 views: Run, Belt Setup, Communication, Alignment, Job and Advanced. After completing the configuration of the camera, we will be able to see the detected products in this Run view. Starting out, we will use it to see if the camera can detect that the belt is moving. The speed of the conveyor belt can be seen under the current belt speed. The first settings to be configured are in the belt setup view. We begin by switching from Run to Edit mode. We first define the encoder settings. If the encoder resolution is known, type it in and press Enter. If it is unknown, it can be calculated automatically. Click on Mark Start Position and let the belt run. Then stop the conveyor belt and click on Mark End Position. Type in the traveled distance and press Enter. Now the encoder resolution is calculated. We continue with the belt setup. With belt detection exposure, the brightness of the image is set. To set up the belt width, adjust the blue region so that it covers the width of the belt where products should be picked. We use the Select tool to modify the size and the position of the region. We save to flash, and the camera now permanently stores the belt position and where to locate the products. In the communication view, we can select the relevant picking system. In this tutorial, we are working with the ABB Pickmaster. In the Picking System IP tab, we type in the IP address of the computer, which contains the robot software. The FTP settings give the opportunity to save images on an external FTP server. Activate the FTP server and choose one of the following options. With None, no images are going to be saved. With Only Objects, only images which contain products will be saved. And with the last option, all captured images will be saved. Then type in the IP address of the FTP server. Now the configuration of the initial settings is completed. We save and switch back to Run mode again. In Alignment, we align the camera's coordinate system to the robot's coordinate system. We use an alignment target printed from the user manual. Measure the diameter of the circles on the printed target and enter the millimeter value. Now, place it very accurately so that the laser line is positioned between the two lines. Click on Start Alignment and let the conveyor belt run. As soon as the target is captured, it is shown in the user interface. In this case, the exposure is too high and the target is not found. So we need to adjust the alignment target exposure. We carefully place the target in the right position again and choose Start Alignment. This time the tool center point and all circles are green, which means that the calibration is successful and we can save the alignment to Flash. The next step is to align the robot with the alignment target. It is very important that the target remains fixed on the belt during this process. Once the target is placed underneath the camera, only move it by running the conveyor belt. Now we go to the job view and select Edit mode. We configure the camera settings to acquire good height profiles. We place the products to be picked under the laser line and adjust the exposure until the laser profile of the products is fully visible but not too wide. Then we need to verify that these settings work for the complete product range. Now we go to the image settings. For a typical application, the needed resolution is in the 1 to 3 mm range. Square pixels means that the resolution across the belt is equal to the resolution along the belt. When not using square pixels, it is possible to set a longer profile distance, allowing for a faster belt speed, while keeping a high resolution and picking accuracy across the belt. For the objects used in this tutorial, we set the image resolution to about 1 mm. The buffer length defines how many millimeters of belt length to capture in each 3D image. But we first set the overlap. We needed to ensure detection of all products on the belt and not risking that any product is captured only partly in one image and partly in the next. For each image, the last part of the previously captured image is copied in. To set the overlap, we use the longest length of the largest product and add a 10 mm margin to it. As a rule of thumb, we can use a buffer length that is about 3 times the overlap. In object settings, adjust the minimum and maximum limits of the area and the height of the products to be picked. With the Z rotation, we decide how the robot is picking and placing the products. The product's orientation can be detected in 180 degrees or in 360 degrees. 180 degrees can be used for products that are symmetric. For example, a rectangular box. For asymmetric products like these shrimps, we use a 360 degrees, which makes it possible for the robot to place them correctly in the package. If it is not important how products are picked and placed, no Z rotation can be used. There are several height calculation methods that fits to different gripper designs and product shapes. More information on these can be found in the operating instructions of the sensor app. In this case, we go with the Robust Max. This height calculation mode reports the highest value of the product to the robot. If the products on the belt are clustered and touch each other, the cluster is normally detected as one large object. Singulation is an optional image processing step which intends to separate such clustered objects into single objects. This works under certain conditions. To increase the chance for a successful singulation, the area and height limits under object settings have to be set very precisely. Select the singulation method based on the product type. Erosion based. This method improves performance for box or pillow-shaped products. Edge detection based. This mode improves performance for products with rounded upper surfaces. Now all job configurations are done and we click on Save to Flash. And we go from Edit into Run mode again. We return to the Run view and let the conveyor belt run. The 3D belt pick sensor app detects the products and their picking coordinates are sent to the robot, which successfully picks them up. In the advanced view, we see which data was sent to the robot. Thanks for watching this tutorial. Now you have learned how to set up the 3D belt pick sensor app from SICK.